Hello students, welcome to the 20th lecture of this online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on plasmonic nanoparticles as antennas and waveguides. So here is the lecture outline. We will look into some traditional radio wave and microwave antennas. Then we will see how plasmonic nano antennas look like. We will also look into the applications of plasmonic nano antennas, plasmonic nanoparticle waveguides, applications of plasmonic nanoparticle waveguides, and how to overcome losses using gain media in this kind of waveguides. So, radio wave antennas are there in existence for centuries now. So, these antennas are basically an electrically conductive structure that can convert an oscillating current, electric current, into an electromagnetic field and vice versa. So, a transmitter will be able to convert oscillating electric current into electromagnetic waves or radiation, and a receiver antenna should be able to do the opposite of it. So, here are some examples of radio wave antennas and microwave antennas. Okay, they are put into two buckets. So, you remember that antennas are key components in transmitters and receivers of electromagnetic radiation, and we have seen that at radio wave and microwave frequencies, antennas can take the form of metallic wires, poles, loops, microstrips, which are of the dimensions comparable to the wavelength that they are dealing with. Now, if you look into monopole antennas, so these are monopole antennas. So, monopole antennas basically comprise of a single metallic pole, which is of length L, and it is mounted on a conducting plate, and in that case the resonance frequency will be C over 4L. That corresponds to a wavelength of lambda that is equals to 4L. Or you can say that the length of the monopole antenna is L, which is lambda by 4. Okay. So, equivalently you can also have a dipole antenna which comprises of two poles. Di means 2. So, there are two poles which are separated by a small gap, as you can see here. Okay. And each of these poles are of length L, and again L is lambda by 4 when this antenna will show resonance. There are other types of antennas as well, loop and microstrip. We will not go into details of those. Okay. We are mainly focusing on this dipole kind of thing and monopole, because we will see their analog in the plasmonic domain, right. So, an antenna may also take the form of an electromagnetic conductive structure that could intercept an electromagnetic wave and can alter its angular distribution. Now, when we come to microwave frequencies, so these are basically microwave antennas, okay, and in that case they are looking like a horn. So, this is a metallic horn that will be connected to the end of a waveguide. So, this is where the waveguide ends, and this is the horn kind of metallic horn kind of shape. So, this is a horn antenna. And you can also have a dish antenna, which is I believe everybody has seen dish antenna. This is basically a paraboloidal metallic surface that is basically a reflector, and the end of the waveguide which is carrying the signal this way or that way. Okay. If it is a transmitter signal, so the signal is coming from the waveguide and then it is reflected onto the reflector and then it is going out. Okay. And if it is a receiver antenna, so it does the exact opposite. Okay. So, in this case the location of the waveguide is exactly at the focus. Okay. Now, these antennas are not necessarily resonant, and their dimensions must be substantially greater than the wavelength of the radiation. So, that is the difference between the monopole dipole antennas, that is the radio wave antennas, and the microwave antennas. Okay. Now, coming to optical antennas or plasmonic antennas for that matter, we will better say optical antennas. Okay. And we will see that resonant optical antennas may be constructed by fabricating metallic structures similar to those of radio wave antennas, and here the only important thing is that we have to scale down the dimension, because the frequency of optical radiation is much higher than the radio waves. So, the dimension, the physical dimension of the elements, antenna elements in optical frequency will also be much smaller. Okay. So, here are some examples of optical antennas made of metallic structures that can exhibit resonance at the optical frequencies, like rod, split ring, double split ring and nanosphere. Okay. So, these are the examples of the resonant optical antennas. Now, at optical frequencies, the optical field interacts with the metallic antennas such as these shown here, rod, split ring, double split ring or nanosphere, via SPP waves, surface plasmon polariton waves, which have propagation wavelength much smaller than the free space optical wavelength. So, that is what we have discussed, that because the surface plasmons have very large wave number, so they can actually support very tiny wavelength, and that is the reason why they allow you to have that they allow manipulation and guiding of electromagnetic radiation in much sub wavelength dimension. Okay. So, in this case you can also see that the length of the optical quarter wave dipole antenna lies in the nanometer regime, right, and optical nano antennas are also there which are non-resonant. So, in that case you can think of metal coated tapered optical fiber tip that is used for near field microscopy, and also there are paraboidal mirror used in telescopes. So, these two things are also possible. So, these are like non-resonant optical antennas, and as you understand that the dimension of these optical antennas are typically far greater than the optical wavelength. So, they are very similar to the microwave antennas you can think of, and these are very close to these are basically sub wavelength antennas. So, they are basically close to the radio wave antennas we have seen in the previous slide. So, these plasmonic antennas operate as scatterers that can convert the incoming light into localized surface plasmon polariton waves that in turn radiate light with modified spatial distribution. So, you can actually decide the directionality of the light beam being scattered, and also you can decide on the spatial distribution of the optical intensity of the reflected or scattered light. Now, metallic nanosphere looks pretty simple as an antenna. So, this is basically an example of resonant optical antenna, and it exhibits resonance when it is illuminated by planar optical wave. Now, why I am starting with this? Because this is nothing but a plasmonic nanoparticle, or you can think of any metallic nanoparticles in optical regime. Okay. And as we mentioned that you can excite localized surface plasmons by direct illumination. So, you can simply shine light on this nano antenna and it will start giving you that kind of characteristics. So, at the resonance frequency, so for gold nanoparticles this lies typically around 520 nanometer. For silver nanoparticles it lies typically around 480 nanometer, right. So, at the resonance frequency the field in the vicinity of the nanosphere gets enhanced and the field also gets localized. So, it is very strong just around the nanoparticle, and that also gives rise to the scattering cross section. So, the amount of scattering by this nanoparticle at resonance become much larger than its geometrical cross section, and that is how they can actually work as an antenna. There are other metallic nanostructures also possible which have got nanoscale dimensions, such as this kind of split ring structure or double split ring structure. They also can be designed in a way to have resonance at optical frequencies, and mind that their properties, their resonant properties are basically shape and material dependent. So, you can get tunability in terms of the resonant frequency where you want your antennas to operate, based on the design and the material of the antenna. We have also seen till now the discussion was on this resonant optical nano antennas, which are useful to localize and couple light into small absorbers. So, you can also think of this kind of structures. Okay, they are able to localize and couple light into small absorbers such as single molecule. Now, in the case of near field microscopy arrangement, where you have a metal rod like this on a conducting pedestal, and that may be placed at a tapered end of an optical fiber, and this can create a monopole antenna, right. So, this will be useful for near field microscopy, and you can also think of another arrangement where a nanosphere is placed at the end of a pointed glass tip, that also carries out a similar function of localizing and coupling light to small absorbers like molecules and all these things. So, in general, resonant optical antenna placed between an emitter and an absorber can enhance. So, these are the resonant optical antenna. They are not, these are the resonant optical antennas, this one and this one. So, they are placed between an emitter and an absorber. So, here the emitter is that molecule, okay, and you can that will emit the light, and this will be the absorber that will catch the light, or it will gather the light, you can say, or collect the light. So, this kind of interaction between the emitter and the absorber can serve to enhance the interaction by facilitating the process of radiation and detection. So, these are some examples of resonant antennas in near field microscopy, right. Now, let us go back quickly to the basics of what happens when plasmonic nano antennas or metallic nano antennas, or you can say metallic nanoparticles, they interact with light. So, if you remember from our previous couple of lectures that metallic nanoparticles have abundance of surface electrons, and which naturally wobble like a piece of jelly. So, when there is an impinging light, when light falls on them, the electric field of the light oscillates at a particular frequency, that is the frequency of the light, right, that you have chosen. Now, when the frequency of the light matches the natural frequency of oscillation of the electrons on that metallic nanoparticle, there will be resonance. So, that resonance we call as localized surface plasmon resonance. Now, LSPRs give rise to a drastic alteration of the incident radiation pattern and to striking effects such as sub-wavelength localization of electromagnetic energy, which we already discussed, that using by converting photons to, you are basically transferring the energy from photons to plasmons, right, and by doing that you are able to, because plasmons have wavelength which are deep sub wavelength, you are able to have sub wavelength localization of electromagnetic energy. You are also able to have high intensity hotspots. Hotspots means the places where there are huge concentration of electric fields. Okay, so these are called electric field hotspots, and you can also find or achieve directional scattering. It means you will not scatter in all the direction, rather your scattering will be only focused in one particular direction. So, that is directional scattering of light. Okay. So, here are some of the examples of typical plasmonic nanoantennas that have been fabricated till now. So, you can think of spherical dipole, you can think of elongated ellipse. So, these are like nano rise or nano, yeah, these are ellipsoidal shape. You can think of single wire, which is basically a nanorod. You can think of dimers, mean there are two particles, two spherical particles. You can think of two wire nano antenna, it's like this is single wire, this is two wire. You can also have nano dot array, so where you place these dipoles in a linear chain. You can have bow tie shape antennas. Here there will be very strong confinement of electric field. You can also have diablo kind of shape. You can have nanorods patterned or placed as Yagi-Uda kind of antenna shape. You can think of spiral nano antennas, you can think of fractal design, you can also think of nano hole array, which are from the Babinet principle. So, these all different shapes have been tried and tested for different applications. Typically, they all have resonance in close to visible range. So, in visible and near infrared range. Okay. So, that was the entire motivation behind studying this kind of structures, because LSPR can also couple the electromagnetic fields emitted by the molecules, atoms placed in the vicinity of nanoparticles, leading in turn to a strong modification of the radiative and non-radiative properties of the emitter. So, you can actually probe a single molecule or a atom using this kind of small dipole antennas. Now, since LSPR enables an efficient transfer of electromagnetic energy from the near to the far field of the metallic nanoparticles and vice versa, they can be considered as antennas, because they are able to transfer energy both ways, okay, and they work in a similar way as the radio antennas, but only difference is that these nano antennas work at much higher frequency range, right. So, what are the materials? As I already discussed, these are plasmonic nano antennas. When they are operating at the optical frequencies, the material we choose are of gold and silver because of their good metallic properties and low absorption in this particular frequency range. So, here is an example of plasmonic nano antennas for unidirectional scattering. So, when we say scattering, you can think of a silver nanoparticle coated with some kind of dielectric layer. Okay. Now, why we require two of these to get a unidirectional scattering? Now, the reason is that you can think of this metallic nanoparticles to have the electric dipole, because you will have the electron cloud moving on top and top and bottom, it can wobble depending on the electric field, right. But the charges will always remain on the surface of this metal, right. That is the fundamental physics that we know from school days. But then when we have a coating of a dielectric layer around this one, there can be a polarization current in this coating, and this circular current will give rise to different magnetic modes, magnetic dipole, quadrupole, octopole and so on. Similarly, here also on the electric on the metallic surface, you can get electric dipole, electric quadrupole, electric octopole, depending on the charge distribution of the oscillation that is taking place. Now, if you remember from the Mie scattering theory, we are able to calculate the scattering cross section of any spherical particle of radius r. Okay, if we know these coefficients, which is an and bn, these are the Mie scattering coefficients, right. So, an is the electric nth order or nth mode electric coefficient, and bn is basically the nth mode or nth order mode magnetic coefficient. So, if you think of making it unidirectional, the first important thing is that you have to ensure that you are getting an overlap of the same order of the electric and magnetic modes, and they are also of the same magnitude, right. So, that is the reason, that is how you will get a unidirectional scattering. So, this is one example of that. So, here A1, B1 are non-zero, remaining all are zeros, all higher order modes are zeros. Okay. It means you are only able to excite in this case electric dipole and magnetic dipole, and if you make them perfectly overlap, you are basically getting a unidirectional scattering. It means you see the scattering lobe is only in the forward direction, there is nothing in the backward direction, right. So, this is a unidirectional scattering. Only problem is that the beam width alpha is much wider. Now, look at this one here, only A2 and B2 are non-zero, remaining ones are 0. It means you are only able to excite quadrupoles. Okay, so when you excite only the quadrupoles and make them completely overlap, the electric quadrupole and magnetic quadrupole completely overlap and they are same in magnitude, you actually come up with this kind of a front lobe. So you see this is much more directional because the beam width is much narrower in this case, but it comes with some additional side lobes. What are these? These are basically the 3D scattering pattern which are cut or sliced, okay, for better visibility. Now when you go to higher order modes like hexapoles or octopoles, okay, so you are able to, that is A3, B3 are non-zero, remaining all are 0, okay. In that case you see you can actually make it more directional, but there will be some scattering losses because the side lobes come out, okay. So this tells us that there is possibility of achieving unidirectional scattering if you are able to do that. Now if you take a practical example of silver nanosphere coated with n equals 2.5 kind of material, and there if you try to see that this is the scattering only from the electric and magnetic dipoles, and you are able to match them here exactly, so, and this is what you will get. You will get a very very much unidirectional scattering pattern that we have seen before at this particular wavelength, right. Now if you consider these are the radius of R1 is the radius for the silver nanosphere and R2 is the radius for this coating or the shell, okay. If you choose a different set of parameters, you will be able to get a match between electric quadrupole and magnetic quadrupole. These are all described here, okay, and if you see that you are actually getting a kind of much narrower one, but then theta equals 0 and theta equals phi, they are not exactly matching because there is slight mismatch between the two things, but that they are very close to each other, okay. And if you compare this with a uniform sphere of dielectric material, okay, so if you take a uniform sphere like this of refractive index n equal 3.4, you will see that you are only getting this kind of mode, okay, and the scattering pattern is actually not unidirectional. So you have scattering in the forward direction, you have scattering in the backward direction. So what is this red and the blue thing? So the red one shows the plot along phi equals 0 and phi equals 90 is shown is along this axis. Phi 0 is this one, horizontal and the vertical cuts you can say, and you can see here that the red and the blue are not overlapping. So there is a perfect overlap here, there is a little bit of mismatch here, and this one is a complete mismatch, okay, because it is not symmetrical, azimuthally symmetrical, okay. So you can also make this kind of nanoparticles line up to make a Yagi-Uda kind of design. So what you can see here that when you just have two nanoparticles, this is a particular this is the beam width, and you have got tiny side lobes which are not so good, and you see the maximum radiation intensity is 1.2 e to the power minus 12, okay. This is a cross section, okay, basically in meter square, and when you make n equals 3, you see the side lobes are getting narrower because you are kind of, you know, this overlaps are kind of making this constructive interference, and then your beam lobes are getting narrower. So this happens with n equals 3. Also the intensity of the beam is also increasing. When you go for n equals 10, that means you have lined up 10 such nanoparticles. So you are working at 1550 nanometer or 1.55 micrometer. The d is the gap between them, that is taken as 700 nanometer here. So when you take 10 such nanoparticles and you shine light from here, you see a very good unidirectional antenna. So the maximum scattering cross section has also increased 7.9 e to the power minus 12, and there is no backscattering. So, that is also perfectly good. So, these are simulation results as well as so FDTD simulation, finite difference time domain method simulation results are shown here, along with CDA, that is coupled dipole approximation. I will not have time to go through but these are like different analytical techniques, this one to find out the scattering calculations. So, they are showing that the simulation results are good match to the theory. It means the way it has been calculated is correct. You can also have 2D plasmonic nano antennas like this. Okay. So, you can have 2D plasmonic nano antennas, something like you have a gold nanorod in a silver nanocuboid, okay, and you can line them up as an kind of array, 2D array. So, there also you can calculate what is the scattering cross section, theoretical and simulation, you can find it out. Here the reason to show this one is that different elements can be also, so each of these particles can be actually modeled as tiny dipoles which are all interacting with each other, and this overall particle is also interacting with another particle. Okay. So, if you look into these two particles, okay, you can think of these two particles lined up here. Now, depending on the electric field direction, so if the electric field direction is this one, so we call this as LE, that is longitudinal edge polarization. It means the polarization is along the longitudinal edge. You will have dipoles created like this, plus minus, and you will have a kind of bonding type of interaction. So, when this kind of interaction happens, the energy lowers and it will redshift. You can also have the other type of interaction when the nanoparticles are placed side by side, and or you can say nano antennas are placed side by side and the electric field is along the transverse direction. You have plus minus, and this positive charges, they are closer to each other now, or the negative charges, they are closer to each other. So, they will experience a repulsive force, and that will actually increase the energy and you will see a blue shift in the resonance peak. Antibonding type of interaction is also seen when you have electric field in this kind of orientation or in this kind of orientation. So, here also you can see that what is happening, these are side by side and electric field is along the longitudinal edge. So, you can have antibonding interaction here, and this is where they are next to each other and electric field along the transverse edge. So, for different gap Lx and Ly, this is Lx and this is Ly, you can actually find out what is the, well, there is a typo here, this has to be Z, this is X. Okay. So, you can also find out. So, LE is nothing but H to H separation, SS is side to side separation. So, for different dimensions you see the resonance peak looks different, there may be new other peaks coming up, but overall they all look like having a resonant wavelength. So, that is how this can work as 2D plasmonic antennas. There are other types of 2D plasmonic antennas possible, like you can have 2D array of gold nanoparticles, spherical gold nanoparticles, or you can have them in other shapes like spikes and so on, dodecahedron. Okay. So, this shape is called rhombic dodecahedron. These are different shapes, but they all actually serve a different purpose here, as you can see. So, if you just think of gold nanospheres, this one, and then if you keep on increasing the size of the spheres, keeping the lattice constant same, you will see that the resonance is getting redshifted in wavelength. That is happening because as you keep on increasing the size of the nanospheres, the nanospheres are getting very close to each other, their interaction is getting very stronger, and that actually gives you this redshift. And when you change the shape from spherical to rhombic dodecahedron to spikes, the spikes will have much more electric field concentration along these spikes because of this lightning rod effect, and you can see that they are able to interact much strongly with each other, and that is why the resonance for the spike one is much redshifted as compared to the nanosphere arrays. Okay. You can also have different applications of this plasmonic nano antennas. One most prominent application is in the field of making solar cells more efficient. So, you can use this metallic nano antennas at the front surface of the solar cell to absorb light, as well as they can scatter light into the absorber layer. So, here the main application is not as absorber, rather forward scatterer. So, they actually allowing the light to actually go into this absorber layer, and whatever is getting reflected, that is again reflected back by this nanoparticle layer, so that it gets a chance to get absorbed. So, that is how the efficiency of the solar cell can be improved. You can also have nano antennas embedded inside the solar cell. So, here they will be acting as absorbers at the resonance wavelength, and they will help you generate more hot electrons. You can also have metal corrugation at the back surface of a cell, and if they are sub wavelength and these are metallic ones, so they also give rise to plasmons. So, they will allow you to absorb more efficiently. So, these are the different methods of improving the light trapping efficiency or light conversion efficiency. So, here is an example that with 3-dimensional solar cell as compared to the nanoparticle cluster solar cell or the flat solar cell, the 3-dimensional solar cell like this with nanoparticles, they are actually having the highest efficiency. So, these are the 3D solar cells what people have tried to make, and they have got the highest efficiency. So, that's a work reported in 2016. Now, things have also improved further. There people are able to go even further efficiency in solar technology. We can also use plasmonic nano antennas for sensing applications. So, how it works, like you have 2 gold nanospheres maybe, and you see that they are, you are going to sense single strand DNA or double strand DNA. So, single strand DNAs are flexible, so they allows these nanoparticles to come closer to each other. When the nanoparticles come closer to each other, your resonance peak will get redshifted. But if it is a double strand DNA that gets attached between the nanoparticles, they are much stronger or stiffer, you must say. So, the gap between the nanoparticles are larger, so it will be a much blue shifted one. So, the spectral shift allows you to do the sensing and tell you whether it is a double stranded or a single stranded DNA. You can also do molecular sensing using the plasmonic hotspots that we have discussed, like plasmonic nano antennas will have a lot of electric field hotspots in between. So, there if you have some sensing molecules and you try to do the surface enhanced Raman scattering experiments, you will get much enhanced effects out of this. So, these are also applications of plasmonic nano antennas. They are basically serving as test beds for SERS, okay, or you can say they are SERS substrate, SERS SERS. Okay. You can also think of waveguides. So, another novel concept of guiding electromagnetic radiation with transverse confinement that is below the diffraction limit, and it is based on the near field coupling between closely spaced metallic nanoparticles. So, if you think of one-dimensional particle array like this, they can exhibit coupled modes due to near field interactions between adjacent nanoparticles, and we have to make sure that the particle diameter is much smaller than lambda, and in that case the light matter interactions could lead to oscillating homogeneous polarization of the nanoparticle volume, and that results in a oscillating dipole field. So, one particle will excite the another particle, this will act as a source for the next particle, and that is how the oscillation will keep on propagating along the length unless it is decayed, because there is some loss associated with each of these particles. So, there will be damping, loss is damping. So, that is where it will propagate to a certain distance and then it will die off. So, here you can see this is basically a linear chain of spherical nanoparticles. So, here you can see that the electric field density, normalized total field density is been intensity is measured here at different positions along this chain. So, gradually the peak is actually getting lower. Okay. So, you have high, low, high, low, high, low and so on, and that is how it has been measured. So, it has been also measured along the transverse and longitudinal direction. So, the transverse one is this one when the excitation is along the transverse direction. So, that is the black curve. So, in that case it propagates even further, and longitudinal excitation is this one when the polarization is along the length of the chain. Okay. So, in that case it propagates a shorter distance. Okay. So, there are examples to prove that. People have done FDTD or finite difference time domain simulation to show all these things. So, consider a chain of gold nanospheres. These are 50 nanometer gold nanospheres, and they are separated by a center to center distance of 75 nanometer, and there is air in between, nothing else. And these are the calculations of the pulse peak position over time. Okay. In this plasmonic waveguide consisting of the spherical nanoparticles for the longitudinal. So, this is the longitudinal polarization, these black squares, and the transverse one is this one when the polarization is along the transverse direction. So, this is this one. So, you can see this can actually sustain much longer. Okay. Yeah, and these are the snapshots. So, this, as you can see, these are basically the propagation along the longitudinal direction, and this is when it is along the transverse one. Here also another set of simulation is shown. So, these are basically time snapshots of the electric field for transverse pulse propagation, showing a negative phase delay with an anti-parallel observation of the phase and group velocities. So, this has been done at different time steps, starting from t equals t naught, then you added a delay with it, that delta t, 2 delta t, 3 delta t and so on. Okay. So, you are able to see the particular, the arrow is showing the movement of the particular phase front, and these simulations, though it is not clearly visible here unless it is an animation. Okay. These simulations also confirmed a negative phase velocity of the transverse modes. Okay. And when you change the shape of the particles from spherical to ellipsoid, there are also changes in the transverse and the longitudinal modes. Those are propagating along these waveguides. Okay. So, the pulse peak positions over time in a plasmonic waveguides consisting of spheroidal particles like this one. So, here the aspect ratio of the particle is taken as 3:1. Okay. So, we are showing the longitudinal as squares, okay, and transverse as the triangles ones, and we are comparing this with the spherical particles. So, consider this case, the black data points. So, the black data points are basically case 1 where the particles, the spheroidal particles are having the same volume as that of the spherical particles. Okay. So, that is the case of this one, the black squares, and you can see the other one, that is the case 2, there is the blue ones. The blue ones are basically those cases when the particles with an increased volume, but they have same short axis. So, in that case the surface to surface spacing is also maintained. So, they are having a larger volume, but the same short axis and surface to surface spacing. So, that is the blue points. So, these also provides you a comparison that when you change the size and shape of these plasmonic nano antennas to form a waveguide, you can actually control the propagation characteristics along the transverse mode or along the longitudinal mode, that also you can decide. So, all these things tell you about the excitation, which excitation you should use to propagate longer and which kind of particles you should take. So, this is an experimental demonstration of a silver nanorod which has got an aspect ratio of 90:30:30, okay, and there is a gap of 50 nanometer in between them, and this is a far field excitation spectra of this kind of chain of particles. Okay. So, the square one is basically the result from single particles, and the triangle ones are basically from the nanoparticle chain. So, you see there is a definite change in the resonance wavelength for this kind of linear chain, right. And the experimentally observed surface plasmon resonance for the single silver rods shown here and the chain of this same nanorods in a closed pack kind of chain arrangement for the transverse illumination. So, in this case the transverse means they are the electric field orientation is in this direction, and that is the difference. You can actually see the excitation wavelengths or energy are different. So, there is a blue shift between the two spectra, and that results from the near field interaction between the particles in the chain, and this you can actually understand from those kind of what is happening when the two particles are next to each other and they have a electric field along this way. Okay. So, you can actually analyze the kind of interactions from that kind of analogy. You can also see or visualize this kind of plasmonic wave propagation along a nanoparticle waveguide by introducing some kind of dye. Okay. So, in order to locally excite a travelling wave on this structure, the tip of the near field optical microscope like this, okay, can be used as a local illumination source. So, this you are only exciting one particular nanoparticle, okay, and then the energy is basically transported along this, and then if you put some kind of dye here, okay, that is able to do some extra like there are some scattering from this, and that can be detected in the far field and which is shown here, right. So, you are able to do some local excitation, you are able to do the energy transport because there is no energy directly illuminating this one. The energy was illuminated here and it has been transported along this chain by this coupling. Okay. So, these black dots are basically the particles, this is where the coupling takes place, okay, and this is where you have put a dye, and you can that energy in the dye will allow you to have some fluorescence, and that can be measured. So, local excitation, this is the SEM image of the plasmonic waveguide, okay, and these are basically the images of the topography and the fluorescence that you can see. So, the image that is shown in this one C show the fluorescent spheres, okay, deposited in the region without waveguides, and here you can actually see the spheres deposited on top of the ends of the 4 nanoparticle chain. So, 1, 2, 3, 4, okay. So, this is the 4 nanoparticle chain, this is the illumination source, okay, and that is how you can actually see the local excitation and scattering. Well, I think they have pictorially shown these as the nanoparticles, okay. The black ones are basically the dyes, okay. You can also see energy guiding and sensing on plasmonic waveguides which are operating at telecom window at 1550 nanometer. So, this kind of waveguide is based on a 2-dimensional lattice of metallic nanoparticles on the thin undercut silicon membrane. So, you can see the SEM image of a fabricated device here. So, the dispersion relation will not go into the calculation of this, but then for this periodic arrangement you can actually find out the dispersion relation, and this is the dispersion relation and the mode profile from the top view and the side view of this device is shown here. And this is basically nothing but a plasmon waveguide on a thin silicon membrane which operates at in the near infrared window, that is 1550 nanometer. We have also understood that these metallic nanoparticles, they are lossy in visible wavelength. So, the propagation of plasmons will not happen infinitely, they will gradually decay, they will lose energy. So, ohmic losses in metal are responsible for the decay of the plasmons when they are propagating through them. So, you can actually compensate for these losses by using some kind of gain media. So, you can think of some quantum dots as a gain media where you can optically pump them, and based on that they will be able to provide you some gain and allow longer propagation of plasmon along this gold nanoparticle layer. Okay. So, sorry, it is a gold layer which has got quantum dots through this PMMA. So, there is a PMMA slab which has got this quantum dots. So, you are putting optical pump on this. So, that is how you can increase the propagation length of plasmons propagating on this gold layer. Fine. So, you can see the intensity profile along the ridge, and this is how it decays. So, you can also see the propagation length, how it increases with the pump irradiance. So, when there is pump, it can actually go to a very long distance, like up to 17 micron. Okay. In other case, it actually dies down much faster. So, you can actually use optical gain media to overcome the losses and allow surface plasmon wave to propagate much longer. So, optical field confinement also increases with optical gain, and the presence of the gain can lead to a complete vanishing of the denominator, and you will get a very large propagation constant. Okay. So, with that we will stop here today, and in the next class we will see plasmonic nanoparticles in other applications. So, if you have got any queries or doubts on this particular lecture, you can drop an email to this email address mentioning MOOC on the subject line. Thank you.